Alright, hello everybody and welcome to another new video on this channel. Now you'll notice I designed some things on the channel. I changed the name of the channel, the logo. Hope you all like it. And I really guys support you. Thanks a lot for all the views on the last video, comments. Let's see if you guys are also gonna like this video. Second video on quantum mechanics titled Quantum Superposition. Alright everybody, so now just to bear with you, the whole idea of quantum superposition arises from somebody called Schrödinger. Now you might have heard of this pal before, Erwin Schrödinger. He actually put one of the most important equations in quantum mechanics. This guy over here. And I'll be going over him in complete detail in the next video when we talk about psi of x, which is nothing but wave function. But let's get back to Schrödinger. So the connection here between Schrödinger and the superposition is that the superposition actually is nothing but a linear output of the function psi of x. Whoa, what is all that fancy gibberish mathematics? Well, you know what, let's put the math aside and let's think and observe. Now bear with me and focus on the word observe a bit. So, in reality, we have atoms, right? So atoms, they exhibit this stage naturally, where sometimes they just excite and they're like in a state of excitation and non-excitation. Now think of an atom as exciting as, for example, somebody jumping up and down. So like here's the atom exciting and here's the atom in a non-excitation state. So here's a non-excitation state and here is an excitation state. Alright, now you see the atom here is exciting. It's kind of jumping up and down and shaking a bit, and here is it in a non-excitation state. That is the idea of superposition. We discovered that in order to determine whether this atom has a superposition, whether it exhibits a superposition, is that if you got an atom over here, alright, in order to test this, you shoot at it an electromagnetic wave. Now you took in nuclear chemistry that an atom sometimes casually just emit a gamma particle. Now what is a gamma particle? You see here you have a nucleus and here you have the protons and neutrons smushed together due to the strong force between them. Forget the electrons, but here they are if you want to focus on them. You have some electrons, E. Say this is K, because it can only withhold 2 electrons at most. So anyways, you have some electrons here, and you have the protons and the neutrons. Obviously protons are positive, neutrons don't carry an electrical charge. But sometimes the atom will casually just boop, sometimes it'll emit something called a gamma particle. In this order to stabilize the atom, because some atoms are gonna get ripped apart from each other due to the strong force, because the atom's like, oh damn it, I'm too heavy, dude. I have so much, like I have a whole party going on here. Like look at the amount, and then my nucleus is unstable, like the uranium. Matter of fact, in order for the uranium 235 atom, if you've heard of it before, in order for it to stabilize, it must emit an alpha particle, which actually has this letter, but it is nothing but a helium nuclei. How? Because it consists of 2 protons, right, and 2 neutrons. And that's what the uranium does. It emits an alpha particle to stabilize its nucleus. And some atoms do the same thing, except they emit a gamma particle. Now you might have heard of this Greek letter before. And the gamma particle is nothing but some sort of electromagnetic wave. Just like light, or these radio waves that we sent out in space in order to contact with anybody. And now this wave, it has a mass. It's kind of like a photons. Now the photons of quantum mechanics, now if you really major quantum mechanics, you're gonna learn that photons kind of do have mass, but it's nearly negligible like the electrons. It's even, I think it's less than the neutrino, but the neutrino actually is the smallest of the smallest. But forget the neutrinos, forget all of that, focus on the gamma gamma thing. So let's say that we shoot out a gamma particle, and a gamma particle, like I told you, it's nothing but an electromagnetic wave. Now, what is a wave? We explained it in the last video. So here I shoot out a gamma particle at this pal over here, at this particle. And let's continue. Continue this. Yep. And I shoot it at this atom. You see, if the atom enters these two states, now remember, we naturally find an atom either in an excitation state or a non-excitation state, only one at a time. Only one of these. Only one of these. These are this or this. If you shoot it, right, and you measure, you'll see that somehow this atom can be in both states, in an excitation state and in a non-excitation state. Yep, that's superposition. And thus, this allows the atom to be not in one place, but in two places at the same time, which is why it's called superposition. Instead of the atom being at x1, no, buddy, it can be an x2 at the same time. But you're gonna ask me, well, why don't all atoms, exhibit this? Well, I just told you they do. Every atom exhibits either an excitation state or a non-excitation state. But there are some conditions. Alright? Well, like I said, focus on the word observe and focus on the word measure, because it's really important and it has a different meaning. When I say measure, when I say observe, when I say, for example, observe the atom, take a second to think. If you thought that I meant observe by actually looking with my own eyes at the atom, sorry, I tried to draw an eye, sorry, and I'm an expert. If you thought that by observe I meant to actually look with my own eyes and shine some photons at it, no, that's false. Come on, can you see an atom? Listen, bro, even if you have an electron microscope, you're still not going to be able to see the electrons or the protons. Trust me, dude, these particles, they are insanely small, guys. That's why quantum mechanics is hard. It's not easy to learn. But anyways, forget that. By observe, I mean, in other words, we make a measurement. We make some sort of measurement on the particle. And that measurement may be, for example, getting its spin and its angular momentum, and I'll talk about the angular momentum in the video that's after the wave function in precise detail, because I'm going to be talking about some of the particles, the Higgs boson. But anyways, for example, getting its spin or its angular momentum, that causes the atom to know you just collapsed the atom superposition. See, instead of it being at two positions, when you make some sort of measurement, for example, its spin, its angular momentum, you collapse the superposition. It's in one state. So think, for example, if you're trying to figure out the superposition of an atom, think of it as like a burglar. You feel like, oh man, the burglar, I don't know where it is. It's the exact same thing. If you have a burglar in your house and you're 50% sure he's somewhere, then there must be another 50% probability of him ending up somewhere else. That's the same thing. And what happens when you actually find him? The other 50% dies. Same thing exactly with atoms. We know for certain that the atom is in a superposition. Why? Because we shot a gamma particle at it, and we realized that it could excite and not excite at the same time. So we know without a doubt that it is exhibiting a superposition. But where? We don't know. But when we make a measurement, one of those superposition, for example x2, it dies, and we are left with one. And that's why we have some other techniques. For example, we have something called Rabi oscillations. Now, what is Rabi oscillations? It tells us whether this thing actually has superposition. How? Let's make x y-axis, y x-axis. Now, these Rabi oscillations, they're kind of weird, but let's see, one large. goes on. You have these other ones, and you go out, and then go out, and then you have other ones, and then you go out, and then you go out, and so on. Now, these rabbit oscillations, you'll notice something. As time flows on, these rabbit oscillations, see these kind of waves, they're oscillating, they're going up, down, up, down, up, down. Yep, I know. They're getting less, right? And they're close to zero as time moves on. Why is that? Why is that, guys? So, in other words, are you telling me that because of the rabbit oscillations, because they do this? Now, if you're still confused, the rabbit oscillations are nothing but the measurements that we make on the atom. It shows us whether it's in a superposition or not. So here it's in a superposition, here it is, but it's going less over time. Why is that? It's going less over time because, guys, there's something you also have to realize. Yes, an atom is never alone in a quantum system. There is quite literally no near empty quantum system. Sorry, in other words, there is no perfectly near isolated quantum system of one atom. That's just quite literally impossible. You're gonna have some, I don't know, molecules, some other atom. Like, for example, this is the particle. Let's call this particle A, particle B, particle C, particle D. I'm trying to test my theory of superposition on particle A. Well, bro, particle B, particle C, they're gonna collide. They're gonna have some collisions, make a new particle. They're gonna emit some particle. All of this stuff affects your subject, which is why the rabbit oscillations start to disappear over time. Why? The superposition gets affected by these guys, and that is also a proof that the superposition theory is true. That proved because the atom doesn't just do that all of a sudden. The rabbit oscillation don't just do that. No, there's something interacting with the atom. So there's something in the quantum system. And yes, we can make measurements even way better than this, but you know, just not to get into the too details. If you really want to check this out, well, bro, you should major in quantum mechanics and learn quantum computing, quantum electronics, and stuff. Anyways, so back to where we were. As I was saying, why is this? Because there is no near empty quantum system. You're always gonna have some other particles interacting with your guy, and we have a term for this. Let's say that this x is the time. This, we won't call it regular time, no. We're gonna call it something. Yeah, wait for it. Wait for it. Wait for it. Wait for it. It has a cool name, okay? We're gonna call it the decoherence time. Oh. What does decoherence mean? Decoherence is a really important factor as well, because not everything in the quantum mechanics world is actually perfect. Quantum mechanics, matter of fact, is incomplete. It doesn't explain correctly why the wave function collapses, and we'll get to that in the next video. I know you don't understand, but I'm just giving you key points to really realize why everything in quantum mechanics needs to be studied at some detail so you know what you're talking about, because you have to realize that we use these things in everyday life, so bear with me. I know it's hard. So as I was saying, the decoherence time, the decoherence factor, it arises from something called quantum decoherence. Let's quantum and decoherence for sure. Now quantum decoherence, let's go back to Schrödinger, okay? Schrödinger said, hey guys, I have a thought experiment. Okay, they said, okay, here's Schrödinger. Alright, and he said, hey guys, I have a box. Everybody said, okay, Schrödinger. Alright, what do you got in the box? I have my cats. Schrödinger, what are you up to? What are you up to, Mr. Schrödinger? What are you up to? Listen, I know that's cursed. I know it doesn't look like a cat, but anyways. So Schrödinger said, alright guys, I have a cat over here. Here's its tail. And he said, I'm gonna put with it a bomb. Actually, let's make this box a bit more larger. Larger? Sure, bridge too. I have a bomb here that has a 50% chance. Hold on. That has a 50% chance of decaying. And so decay, Schrödinger. So it's either you're gonna open the box It's either is gonna be dead, 50% alive, or 50% dead. Schrödinger said, okay guys, well, how do we know that? You know how to know that. That's basic. But no, what is the reality behind it? The reality behind it is the superposition. How? If the bomb has a 50% chance of decaying, let's draw a bit large. Here's the bomb, the molecules and everything. Let's say that you have one large, here's your nucleus. The elements inside this, they have a 50% chance of dying, of actually exploding, which means that they also are in a superposition unless measured. Because once you measure and observe, it's either you're gonna realize it's dead or alive. So it's either you're gonna find the bomb, the atoms decay and they explode over time, or you're gonna find it. Check. Cat is alive. Cat is alive. Yeah, like a heart. The cat's alive. It's not dead. So that means that the bomb was in a superposition until it was observed. Now listen, I know this might sound, it doesn't make sense, which is exactly what Schrödinger realized. Schrödinger said, guys, why am I doing this experiment on a cat? A cat has the cat is humongous. The cat is gigantic, quite literally, compared to the tiny particles that we are experimenting on, compared to the nucleus. So Schrödinger came up with something and he called it quantum decoherence. What does decoherence mean? Quantum decoherence is the factor that separates our properties from the quantum mechanical realm. How? In other words, basically, if I have a ball and I have an atom, what is the difference between these two guys? Here's the atom, A for short. Here's the ball, B for short. This ball, I can explain its properties using classical mechanics. However, this pal over here, I can't explain it using I can't explain its properties using classical mechanics. Instead, I refer to quantum mechanics, which is what we went over in the introductory, why and everything, the black body radiation. And that is quantum decoherence. It's the ability for an object to have its properties being explained using quantum mechanics rather than classical mechanics. And decoherence, the part D, just means that you lost that ability. It means that you are out of the quantum mechanical realm. And one of the reasons is you having a large mass sufficient enough to just make you lose your whole quantum behavior. In this case, it's the same thing with the cat. For example, the cat can have a mass of m. The particle, for example, can have a mass of 10 to the negative 40 m. Yeah. It can have an incredibly, stupendously small mass. And guys, come on, we're talking about particles. They're what makes matter. Like, come on. Hello everybody, so as I was saying, we can't operate these quantum experiments on such large objects because they lose their quantum behavior due to quantum decoherence, alright? So, obviously what we did, we came up with a new experiment and we called it the double slit experiment. Now, I'm pretty sure you might have heard about it before, maybe in a documentary or about something like that, but today, I'm here to tell you every single boring detail about this quantum experiment. Basically, we tried to prove the superposition of an object, and we also discovered a new quantum phenomena. It's insane, right? Quantum mechanics is always insane. But anyways, so we have an electron beam gun over here. Let's have some sort of small opening. We have an electron beam gun, and we're shooting from the center here some some electrons, and wow, that looks terrible. Hello everybody, so as we were saying, so in this experiment you take an electron beam gun, so let's call this EG, sorry for electron gun, and you shoot it at two slits, alright? So here you have two slits, you have a wall, and you've got slits in it, some kind of holes, alright? The electron is expected that's gonna go in either one of the slits, so either in this one or either in this one, correct? And over here you're gonna have some sort of screen to detect some pattern. It's either you're gonna have some electrons or you're gonna have, alright, you're not gonna expect this, or you're gonna have a wave interference pattern. What? How can you get a wave interference pattern if you're shooting an individual electron? You're ending up with one electron at one side and you have one. Well, yeah, buddy, that's only when you're observing the electron. That's only when you're making measurements on it while the experiment is happening. If you don't make a measurement on it, let's say this is your eye, if you don't make a measurement on it, if you're not observing, what happens is that the electron doesn't go through one side alone, it goes through both. And what does it make? It creates, when the two electrons meet up, they make a wave interference pattern caused by the two particles. Alrighty? But how can this happen if the electrons are particles? They're whole particles. They're not waves. They're not like the gamma particle. They're not like that, are they? Well, yes, they are, buddy. Now let's just get back to superposition for a second, because this is our last topic of the video. The electron went through both slits at the same time. How? It was in a superposition of both. Both two positions. It was in a superposition at x1 and at x2. It went through both at the same time when we weren't observing. The observer effect wasn't taking place, but when it did, it only appeared as if it was only one electron. See, only one electron pops out. But that's not the case when you're not observing. If you don't actually observe, let's not observe, okay, you're not observing, but boom, all of a sudden you observe, oh my god, why is there a wave interference pattern? Or wave interference pattern. And remember, this only occurs when you're gonna have two particles getting smushed together to make a wave, right? And as I said, go watch the last video because I explained what is the main idea of waves. Now there's something, and it is our last topic in the video. I know, there's a last topic, and you should ask yourself about it. Aren't electrons particles? How can they become waves like that? Good question, and it is what I circled over here. It's kind of like the gamma particle. It's kind of like photons when we talked about the last video. I said that you have the particle. It can have a wave from something called the wave function, which explains it. So when you're shooting the electron from the beam gun, again, let's try it again. You have your electro beam gun. Ooh, that's a nice name, electro beam gun. When you have your electro beam gun and you're shooting it from the center, you're not just shooting a particle, no, you're shooting this particle that has a wave function. It kind of looks like this. Can you see that? Yeah, that's a wave. You have a wavelength in your quantum wave. That is what I have been saying from the last video, and it is actually referred to as psi of x. This is the symbol. And it has something to do with potential and many other factors, but we'll touch on that in the next video in more and precise detail. As always, hope you guys enjoyed the video. Have a good day, and peace.